Impulse. Remember, impulse is F delta T, which is also indeed equal to delta P. Impulse is sometimes given the letter, I think sometimes it's I, sometimes it's J. Not too worried about it. I'm generally just going to write the word impulse. Think about ball sports, like baseball, soccer, or even golf. I'm thinking about sports, ball sport meaning not basketball, although I'm sure it applies somehow, but sports where you're hitting a ball with an object. So in baseball, you're hitting the ball with a bat. Golf, you're hitting the ball with a golf club. In soccer, you're hitting the ball with typically your foot or your head. So how do you get the best hit in baseball? If you want to hit the baseball, what do you need to do in order to get the best hit? What do you need to do to hit a home run? In order to kick the soccer ball as far as possible, what do you need to do to kick the soccer, for the goalie to kick that soccer ball all the way down past halfway down the field? What do they need to do in order to kick it as far as possible? In golf, what do you need to do to get that hole in one? How do you need to hit the ball? What mechanics do you need to think about? So clearly, let's just think about it from a momentum and impulse point of view. In order to get it to go as far as possible, in order to give it the biggest change in momentum, right? That's what you want to do. You want to give it the biggest change in momentum. You want to give it, and we're talking about here not finesse shots. We're talking about getting something to go as far as possible, okay? Finesse shots, like in pool where you're doing trick shots with curves and things like that, or you just want it to go a certain distance. But I'm talking about going as far as possible. If we want it to go as far as possible, the ball, think about what's going on. The ball, in baseball, the ball is coming at you. In soccer, it may be coming at you, it may be still. In golf, it's sitting still. But let's just think baseball and baseball bat. The baseball is coming at you, and let's say we pivot the baseball bat, we're holding it, and we pivot it so that the baseball bat swings, right? The ball is coming at you, and what you want to do is you want to change its momentum. It's got a momentum in this direction because it's got a mass and it's got a velocity, and you want to change that ball's momentum so that before the hit, right, it's going in that direction towards your club or your foot or your head, and after it's going in this direction. And you want it to be going as fast as possible, right? Let's just call that V initial and this V final. And you want it to be going as fast as possible. The change in momentum is going to be mv final minus mv initial, right? Or in this case, it's just a single mass, so it's m delta v. So we want the biggest delta v possible in order to get it to go as far as possible. How do we increase delta p? This really is important for a soccer player, baseball player, anybody playing a ball sport where you want to hit a ball. Okay, if you think about it, well, we want to know how to change delta P and make it as big as possible. Well, we want to look at the impulse that we're exerting on the ball, right? What does it mean to exert an impulse on the ball? We're exerting a force for a certain amount of time. So we're exerting a force for a certain amount of time. When I kick a ball, I'm exerting a force from my foot to the ball, and that force is being exerted as long as my foot is in contact with the ball. When I'm hitting with a baseball bat, I know this thing here doesn't really look like a baseball bat, but stick ball, let's call it. When I'm hitting with it with a stick or with a baseball bat, I'm exerting a force and for a certain amount of time, the amount of time that the ball is in contact with the bat. When we're talking about collisions, we're just talking about those collisions taking as little time as possible so that we can assume that the force is zero. But if we change the momentum, we're clearly not. If we're changing the momentum, where the force is not zero. It's the only way we can change the momentum. So how do we change the momentum as much as possible? Well, we want to increase F and delta T as much as possible. So that's pretty clear. That's pretty straightforward. For anybody who plays a sport like that knows you want as much force as possible, right? So as much force as possible. But that's not the only thing, and this is what somebody who's good at a sport understands, is it's not just as much force as possible to get that ball to go farthest. What else do we need to do? Well, look at this equation. It tells you that we need to exert that force for as long as possible. As long as possible. So that means you need to make good contact with the ball, right? So think about when a ball glances off your bat or glances off your foot or glances off your head, it's not in contact with the object that you're hitting it with for very long. You want a good solid hit right in the center of your baseball bat so that you are in contact with the ball for as long as possible. And that's what gets you to be able to hit the home run versus hitting into the infield, right? Is that you've exerted your force by swinging your bat, and there's only so much you can do. It's just so fast you can swing your bat. But as long as you hit that ball straight on and keep the ball in contact with the bat for as long as possible, you can change the momentum more. And it's the same for a solid kick with your foot. You want it to be a solid kick, and you want your foot to be in contact with the ball as long as possible, etc. So that's impulse. So let's look at an example, a quick example. So I looked up some statistics of baseballs, and what I learned was that a baseball has a mass of about 145 grams. And think about, I think most of us who know a little bit about baseball know that pitches are 100 miles an hour is a good fast pitch. Maybe a fast pitch is going to be 90 miles an hour coming at you at 45 meters per second. We could actually do some pretty easy measurements with some high-speed photography, which you could do with an iPhone these days or whatever kind of phone you have. And if we did some high-speed photography, you could probably figure out that the contact time with the bat is about a millisecond. And that the ball usually, a good solid hit, the ball goes off a little faster than the pitch in the opposite direction, 110 miles per hour. Notice I didn't put vectors on here because, or I could put a vector sign and say that the ball is coming at you, and then the final velocity, the ball is going away from you. If you're going to hit it with a baseball bat. So these are statistics. I think that they're statistics for sort of a major league baseball player or a good baseball player. So again, the ball, here's your bat. I know bats don't really look like that, but here's your bat. The ball is coming at you at the initial, and you hit it, and then it's going to go away from you, the final. And so the question I have is how much force does that baseball bat exert on the ball? What is the force exerted on the ball, right? In other words, it's a measure of how hard those baseball players hit that ball. And we could do the same for any sport. We could do the same for soccer balls. We could do the same for golf balls. The speeds would just be a little bit different for each. So what is the force? Okay, so what's the force of the hit? Okay, so I'll go to a new page, but I'll just write it here. We're just going to use that impulse. Again, we're going to assume that the force is constant throughout the hit. Might not be a good assumption, but it's an average force. It's a good assumption that that the average force is constant because the average force is constant. So we can say that the average force times delta t is equal to delta p. And again, if we had a variable force, we would have to integrate both sides. Right? I'll just say it. I'll say it, but we're not going to do it. F dt equals the integral of dp, which is still delta p. But as long as we talk about average forces or constant forces, then we're going to get that. Okay, so let's go to a new page and do this. So we've got F delta t equals delta p. So therefore, the force is equal to delta p over delta t. And now it's really just a plug-in. Well, it's a little bit more than a plug-in. So remember, the ball was coming at us vi in that direction. We got to choose a direction as the positive x direction. I'm just going to naively choose the initial direction as the positive x direction. So that means that the final is going to be in the negative x direction. And so we can write this out as delta p is mv final minus mv initial over delta t. And so we can start plugging in the mass of the ball, which is 145 grams, v final. And yeah, we probably want to change that to kilograms at some point. Let me just look at it. Yeah, 145 grams. The final was 55 miles an hour, 55 meters per second, but it's in the negative x direction, right? So it's negative 55 in the x direction minus, you got to carry those minus signs. I look at your quizzes, and so many of you are just not using minus signs correctly. You're not carrying your minus signs. You're not thinking about your minus signs. You're not thinking about what should be negative. It's just math. You've got to, if a minus sign's there, you got to use it. 145 grams times V initial, which is positive 45. Sorry, I ran out of room. Wait, let me rewrite this. Okay, I rewrote it. So the final velocity is in the negative x direction, negative 55 meters per second I. The initial velocity is in the positive x direction, 45 meters per second I. So we plugged in for mv final minus mv initial on top. Delta t was 1 millisecond, which is 0.001 seconds. And so now it's just a plug in, carrying our vector signs, right, so that we know the final direction of the force. So the answer, if I just plug all that in, is we get negative 1.45 million? No, 14.5 million. But remember, the units are grams meters per second. Negative being negative I direction. It's going in the negative x direction, right? We just drew that right above here, right? It's going in the negative x direction because we chose plus x to be the direction of the initial direction of the ball. But this is grams meters per second. It's not newtons. We want to divide it by 1,000 to get kilogram meters per second or newtons. So it's negative 14,500 newtons in the x direction. Yeah. So it's the force is 14,500 newtons. That's a huge force. That's a humongous force that bat is exerting on the ball. It's amazing that the ball doesn't just shatter into pieces. But you know actually what happens to a baseball is it squashes. It really squashes like an orange. It only does it for a millisecond, so you miss it. You generally don't see it, but it really squashes. Look on YouTube for pictures of baseballs getting hit slow-mo. It's pretty cool. I mean, that's a big force.